Hi there! Whether this is new for you or just a review, welcome to the fundamentals of logic. In part 1 we saw some of the basic ideas that make up our system of logic, and in this part we'll start to look a bit at how they all move together. The first half of the video will look at truth tables, which are our first way of really analysing truth values. The second half looks at some key concepts which help us to explore more complex examples down the line. Let's quickly review though the statements we saw last time. Here they all are. I won't go through them all again now, but I will be using the symbols that are in red on the list opposite. I will use capital letters for simple statements, mostly P, Q, R and S, but it doesn't matter. Sometimes if you're working on a problem, people will set up rules for how to choose letters at the start of the alphabet or in the middle and so on, but we don't need to do that right now. So logic is our system for following true and false. Sadly though, in real life, finding true or false is not always easy. How do we follow truth values carefully through long and very detailed arguments? One way is by using truth tables, which can compare different situations. Truth tables are our first look at logic working like a machine. Here is the truth table, which shows us simple statements and negations. A simple statement can be either true or false, and the negation is the reverse of that. So if we read along our two rows, we can see that when P is true, not P is false. And, say it with me, when P is false, not P is true. More complex statements have more outcomes, but how many outcomes? Think about it for a moment. If I make a compound statement with P and Q, how many different combinations of true and false will there be? What about a compound statement with three letters, P, Q and R? Pause if you want to think about that and come up with a number. I'll tell you the abstract answer first as a hint, and then we'll see how it works. A compound statement with n simple statements will have 2 to the power of n different true or false combinations. We can show what's happening here with a tree diagram. Let's start with P, and we know that P is either true or false, and so that is 2 outcomes. If we move on to Q, Q can be true or false either way, no matter what P was. So that means for each outcome of P, we have 2 outcomes of Q, 4 outcomes altogether. If we add a third statement, R, then this doubles again, so there will be 8 possible outcomes. Every time we add a new statement, we are doubling the number of outcomes. We are multiplying by 2, because there are 2 possibilities, true or false. So we've shown that with 2 simple statements there are 4 possible outcomes, and in the tables below I'll list them in this order. The first row will be where P is true and Q is true. The second row will be true and false. The third row, false and true, and then the fourth row will be where P is false and Q is false. It's helpful to be able to remember which row is which, but you can always check on the tables if you need to. We can now look at the conjunction, and here is the truth table for that. When you speak a conjunction, for example, today is Wednesday and I am hungry, that will be true if both of the simple statements in it are true. Otherwise, it will be false. So a conjunction is only true on the first row, but false on the other 3 rows. If that is quite clear to you, then feel free to skip forward this slide, but let's just look at all 4 situations. In the first, it is Wednesday and I am hungry, so the whole compound statement P and Q is true. In the second row, it is Wednesday, but I'm not hungry, so the overall compound statement is false. And in the third row, it's not Wednesday, even though I'm hungry, so again, the whole compound statement is false. And then finally, on the fourth row, it's not Wednesday and I'm not hungry, so of course the statement to say that I am, or it is false. We should be able to think through all logical statements this way, although once they get really complicated, we usually can't. But I'll leave you to do this in the next example. A disjunction is a bit different because it can be true when only one of the simple statements is true. So the results of our truth table are also different. An inclusive disjunction is the most common and says that at least one of them is true, but maybe both. So this statement is only false if both statements are false, which is on the fourth row. The exclusive disjunction is true if just one of the simple statements is true. It cannot be both. So the compound statement will be false on both the first and the fourth row. Now we come to the conditional, and things get a little spicy. The conditional of P into Q is the same as saying the sentence, if P is true, then Q is true. Again, we have 4 rows in the truth table, but the only way we can know for sure that this is false is if P is true and Q is then not true. This is row number 2, but the other 3 rows are a little bit strange. We don't know they are false, but does that mean that they are true? Have a look at these 3 statements. What do you think of them? They probably look a little bit strange to you, right? They are all written as conditionals, but there really doesn't seem to be any link between the first and the second part. But according to the truth table for conditionals, all of these statements are actually true. Is this really right? Does it make logic look kind of silly? Well, a little maybe, but the quick answer here is we are mostly sure that this truth table for conditionals is correct, and it does work as long as there really is a link between the antecedent and the consequent of the conditional. But this is an area of debate. To make it clear why we do say that those rows are true, let's go through the cases, and again, if you are confident, you can skip forward this slide. Say I tell you, if you get me some food, I will give you 100 baht. When is this statement a lie? There are 4 situations, of course. On the first row, you did get me food and I paid you. I did not lie to you. In the second row, you did get me food, but I don't pay you, so I definitely lied to you here. On the third row, you don't get me food, but I still give you money, which is a bit weird of me, but technically what I said to you was not a lie. And then finally, on the fourth row, you don't get me food and I don't give you money. But again, I still didn't lie to you because I only said what I'd do if you did get me food. Finally, let's look at the biconditional. If we remember that the biconditional is 2 reversed conditionals, we'll see that a lot of the same arguments apply. We know that the biconditional can be false in 2 cases, on the second and the third rows, because the biconditional claims not only if P then Q, but also if Q then P. Aside from that, the reasoning will be exactly the same as with the conditional. We will come back to truth tables in part 3, but for the rest of this video, we'll look at a few key ideas of logic that are important to know before we try to go to the next level. As we've seen, the way that we write logic is quite similar to the way we write arithmetic. Some of the vocabulary is the same, but some is a bit different. In arithmetic, if we write 2 plus 2, we call that an expression. If we balance the sum on the end, then we have an equation, 2 plus 2 equals 4. In logic, any set of statement letters and connectives in some order is also called an expression. And if we put several expressions together into an argument using the double turnstile we saw last time, we call this a sequent. We won't look at sequence very much until part 3, but I just thought I'd bring them up now. And while we're here, it's a good time to talk about jargon. In any subject, jargon is the special vocabulary that you need to understand the subject fully. If you don't know the jargon, a different subject can really sound like a different language, but it also takes some time to learn the jargon. I am trying to make this video as simple as possible, but logic is very abstract and the jargon is about things that are not really like anything we know in the real world. So the concepts can be quite hard to get clear in your mind, but we do need to make a clear definition of some of these things. They are different things. So there will always be some jargon involved in learning any subject, and it might take some time to learn. You can watch this video again or try other people's explanations to help you clearly understand the difference, as well as why the differences are important. And on the subject of jargon, let's talk about syntactic ambiguity. Wait, stop, don't run away. Let me go through it. If something is ambiguous, that means it does not have a clear meaning or purpose. We can see it in two or more ways. And syntax is the system of word order for a language. It is a part of grammar. A statement is syntactically ambiguous if the grammar it uses gives it several meanings. So, for example, I will run 6 kilometers, or I will play football and I will eat pizza. Is this sentence a disjunction or a conjunction? In everyday language, a comma or a tiny pause might tell us, but there would still be some uncertainty. With logic, we do what we can to try and make things clear and unambiguous. If we look at the words or and in the example, then the sentence has two obvious meanings. Either I choose a sport, do that sport, and then eat pizza afterwards, or I have to make the choice between a 6-kilometer run on one hand and football and pizza on the other hand. Look at the letters given above. How do you think these two meanings would be shown differently in logical symbols? Pause if you want to think about it, but if you need a hint, then look at the title of this slide. So the sentences would be written differently like this. We use brackets to separate the parts of an expression, and we do the bracket first just like in arithmetic because it is just a small part of the whole expression. With that in mind, which one of these is a disjunction and which one is a conjunction? I'll show you that they are this way round. The statement is of the type that is outside the brackets. To show that, let's say it again slightly differently. When we use a bracket, everything inside the bracket becomes one object. If we make that one object and look at the expression again, we can now see why we call it the type outside the brackets. This top level expression is called the main connective, and it can be difficult to spot sometimes in very complex expressions, as we'll see in just a moment. A side note, but I just want to mention there is nothing special about the connectives we've got. Connectives are words that connect expressions, and we've seen they can come in different types. For example, a negation acts on just one expression, but a conjunction must connect two expressions. Other connectives could exist, maybe even tertiary connectives that need 3 expressions, or quaternary connectives that need 4. How far can we go? Well, how far do we need to go? For the logic we are looking at, we only really need the connectives that we've already looked at, and not all of those. But it's important to remember the options we have at the highest level of abstraction. So brackets in logical expressions help us to avoid ambiguous statements. This works just like brackets in arithmetic, and just like arithmetic, logic has an order of operations. We do this by putting connectives in a hierarchy to see which ones are the most important in expressions. The order we use for connectives is that biconditionals are the most dominant connectives, followed by conditionals, then conjunctions or disjunctions are at the same level, and finally negations are the least dominant connective. A more dominant connective is more likely to be the main connective of the expression. If you want to change that, you must use brackets. Anything inside a bracket is less dominant than what is outside. But if there are no brackets in an expression, then any biconditionals are the main connective. Finally, if there really are two or more equally dominant connectives in an expression, then you work from left to right, making the main connective the one that is on the right. But we generally try to avoid this rule. For longer expressions than the basic ones we've looked at, you find the least dominant part and then work up to the most dominant to find the main connective. This means that you will get to the main connective last as long as you followed all the rules correctly. Again, this is a lot like BODMAS in arithmetic. Another way of saying this is that the main connective has the greatest scope on the expression. Scope is another thing we might come back to, but think of the word telescope. A telescope lets us view a greater distance. The scope of a connective is the view of a connective over the expression, and the main connective is the one that can see the whole expression. In other words, it has the greatest scope. Let's look at a few examples. If you like, pause the video and try to find the main connective in these logical expressions. If you aren't sure yet, don't worry, I'll go through them quickly, and if you do have any questions, you can put them in the comments section. Number one, the negation in this expression only works on Q, and so the whole expression is the disjunction, which is more dominant. In number two, the disjunction is in brackets and we deal with that first, so the whole expression is a negation. In number three, the conditional here would be the most dominant, but it's in a bracket. The negation only affects R, and so the whole expression is a conjunction. In number four, there are no brackets, so the most dominant connective applies. The whole expression is a biconditional. In number five, there is a bracket, but everything inside it is already less dominant than the conditional. This expression would not change if we removed this bracket, but there's no harm in putting it in, especially if it helps you to understand the expression more clearly. In number six, here we have two biconditionals and no brackets. We must fall back to working from left to right. So the expression is a biconditional either way, but it's technically the one on the right. In number seven, there are two sets of brackets, so anything between them is going to be more dominant. The negation only affects the left-hand bracket, so the whole expression is a disjunction. In number eight, there is a bracket around a longer expression. The only thing outside the bracket is the negation, so the whole expression is a negation. For number nine, the negation affects the bracket, but not the whole expression. The whole expression is a disjunction. And in number 10, this one has nested brackets. The biconditional is outside one set of brackets, but still inside the other one, so it's less dominant than the conditional, which is outside. The whole expression is a conditional, the one on the left. Now let's come back to conditionals with a little bit more detail. We've learned about the conditional and the biconditional, and we learned how their truth tables look, but how are they related to each other? This leads us to different types of condition, necessary conditions and sufficient conditions. To see how they work, let's think about a running race. Jim is in the race and he wants to be on the podium at the end. Now, think of three different conditions for Jim finishing the race. The first condition is, Jim finishes the race in first place. Great job, Jim. The second condition is, Jim just finishes the race. We don't know where. And the third condition is, Jim finishes the race as one of the first three runners. What is different about these three conditions, and how do they affect Jim getting onto that podium? In the first case, Jim finishes in first place, so he will definitely be on the podium, but he could have been on the podium if he'd finished second or third. So finishing in first place is a sufficient condition for being on the podium. It's good enough, but it's not necessary. For the second condition, we know that Jim cannot be on the podium if he doesn't finish the race at all. But even if he does finish the race, he might come last or some other position that's not on the podium. So finishing the race is a necessary condition, but not sufficient. Finally, what about finishing in the top 3? Well, the top 3 is what the podium is for, so of course Jim will be on the podium if he meets this condition. And the top 3 is what the podium is for, so of course Jim will not be on the podium if he does not meet this condition. So finishing in the top 3 is both a necessary and a sufficient condition for being on the podium. We can show these 3 different situations in language with the terms if, only if, and only if. If shows a sufficient condition, only if shows a necessary condition, and if and only if, which can also be written as if, shows both. So from our example, if Jim finishes in first place, he will be on the podium. Only if Jim finishes the race, he will be on the podium. And if and only if Jim finishes in the top 3, he will be on the podium. But language is very complex and there are many ways to say the same thing. Here are just a few of the more logic-y ways that English can form a necessary condition. A is a necessary condition for B if and only if B cannot happen without A happening. Or only if A, then B. Or A being false guarantees that B is false. Or if B is true, A must be true. Notice that I said if and only if there. What we're looking at here is a list of necessary and sufficient conditions for being a necessary condition. We're using the ideas of logic in our explanation of how logic works, which is really weird, but we kind of have no choice. That's what an explanation is. Here is another list. A is a sufficient condition for B if and only if A cannot happen without B happening. Or if A, then B. The truth of A guarantees the truth of B. Or if A is true, B must be true. You can see that the 2 lists are similar but different in subtle ways. And then think about how everyday people talk in conversation. We communicate conditions in endless different ways, and this makes life a bit complicated. Look at this table of the very simplest definitions of necessary and sufficient conditions. Even here, you need to be careful. Some forms put B before A, others put A before B. Conditionals can technically be written in either direction. And even though IFF is a very sensible way to make a shorter version of if and only if, it may be a little bit confusing. Don't expect to get all of this perfectly the first time and expect to make mistakes for years to come. Just remember to be careful when you're talking about conditions in logic. And once again, remember that this is all before we look at the many different ways that people express conditions in natural everyday language. We've now looked at all of our basic truth tables and we've looked at the tools we need to decode any basic logical expression and decide on its truth values. We'll talk a bit in more detail about how we do that in part 3, but I hope now you've got some idea about how these areas of logic work. Hi, hope you found that interesting. Like, comment, subscribe, etc. If you prefer shorter videos, you can find this cut up on our other channel just up there. But whatever you do, please keep learning something because no matter who you are or how old you are, every day really is a school day. Bye for now.